We can move to Giorgio Nicoletti. Giorgio got his master's degree in physics at Padova University at the Laboratory of Interdisciplinary Physics with Amos Maritain and Seminar SIFS. He is now doing his PhD, applying concept of statistical physics to neuroscience and ecology. And recently, he has focused his interest to information theory and provision of information theory, I believe. So please, Giorgio.
Thank you. Let me share my screen. Can you see it?
Yes.
Okay. Thank you very much for the invitation. Today I would like to talk to you about a project that we started more or less a year ago, and that deals with the possibility of applying tools from information theory to systems that are usually studied in statistical physics, such as complex systems. So to set the stage, let me just give you an idea on what kind of systems we have in mind. Ideally, we want to study a system that maybe has a large number of degrees of freedom, which are represented by the gray dots here, and which often these degrees of freedom are coupled to one another through, let's say, pairwise interactions, which are these black lines here. And on top of this, we consider that our system lives in some kind of environment that maybe it is as much complex as the system itself, and it's usually quite hard to track, to analyze. So these environments often evolve in times, and ideally they affect all degrees of freedom in the same way. So what happens is that the presence of shared environments creates effective dependencies in the system, which are represented here by these colored lines. And as we will see later on, these dependencies can be quite important. And on top of these, of course, interactions are the key ingredient that shape the behavior of the systems. And of course, in these internal interactions between the degrees of freedom will also create non-trivial dependencies in the system. So we have both this interplay between environment and interactions. And then finally, it is often the case that we don't really want to describe all of our degrees of freedom, maybe because we can only observe some of them, or maybe because it is much more useful to model just a subset or a coarse-grained version of them, which describes the properties that we are interested in. So in general, this is the kind of systems that we consider with these multiple layers of complexity appearing. And even if it's quite an archetypal description, we can actually describe a variety of real-world systems in this way, in particular with respect to the coupling to the environment. So let me give you just a few brief examples. One of them is, for instance, ecological networks, in which our degrees of freedom would be species and the environment would be climatic stress or seasonal variations and whatnot. And then we can consider, for instance, neural systems in which you have neurons and neural populations that interact with highly non-trivial interactions among them, but are also subject of feedback loops or external simulation. And that, of course, will be extremely important in shaping the neural activity. And finally, or for instance, we can consider chemical processes in which you have your degrees of freedom that are molecules or proteins, and you have thermal variations and shocks that kind of change their behavior. In this talk, I will try to show how information theory can help us tackling these problems by focusing on much simpler cases that serves as a kind of proof of concept for these systems. And the talk will be mostly divided in two parts. The first one deals with the problem of disentangling the dependencies that arise due to the shared environment and internal interactions, which in principle may be very, very hard to distinguish. And let me give you a brief example of this. So, for instance, consider that you may have two particles diffusing, for instance, in a two-dimensional space, confined, for example, by an harmonic potential. And I can tell you that in one of these two animations, the particles are really interacting with one another, but in the other they are not, and they only share the same fluctuating environment. And as you see here, it is not obvious at all which case is which, because maybe the particles are kind of moving together intuitively because they are interacting, or maybe because the environment is changing for them both. And the reason why it is so hard is that these changing environments induce dependencies that can mask the ones that are created in the interactions. And in this case, for instance, the left ones are not interacting, whereas the ones on the right are. And you know, if you only had access to the trajectories, or for instance to the stationary distributions associated with these particles, it might be extremely hard to know which case is which. So the first question I will try to answer is, can we disentangle the dependencies created by changing environments and by internal interactions? And we'll try to use information theory to do so. And the second part of the talk instead deals with, if you wish, the second step of this process. So if you want to describe, let's say, a subset of our system with a suitable effective model, what can information theory do to help us? And so can we use it to define optimal effective models and to understand, of course, their properties, maybe in relations with the properties of the original system? But okay, at this point, you may be wondering, all right, but what is information theory in the first place? Well, loosely speaking, information theory deals with probabilities and probability distributions, and it tries to define their properties in terms of the information one can get from such probabilities. And to give you some key concepts that we will use, imagine that you have two probability distributions, P and Q, and you somehow want to understand how similar they are with one another. And information theory deals with questions like this one. In particular, a key quantity for us will be the Kullback-Leibler divergence, which is this quantity here, and quantifies how much the two distributions are different by measuring the information we lose when we use Q of X as an approximation for P. So notice that this is not symmetric, but in general, you can loosely think about this as a distance between the two distributions, which is formally not correct, but it kind of helps with the visualization. And a particularly useful kind of Kullback-Leibler divergence is the mutual information. The mutual information is this kind of distance between the joint distribution P of xy and its factorization Px times Py, where Px and Py are the marginal distributions. And of course, this would be the distribution we would use if the variables were independent. Hence, the mutual information quantifies exactly the dependency between the two variables in terms of how much information they share with one another, which basically means how much information we lose if we assume wrongly that they are independent. And notice that this is zero if and only if the two variables are independent. All right, so with this in mind, let's move with the first problem. Let's try to understand the first problem. And what I will show you here is the core of the work of a work that we published in November in Physical Review Letters. And we'll describe probably the simplest case we can really think of, which is the case of linear interactions. And however, we have some particles that interact, but they also live in a shared environment. And let me be more precise about this. So the interaction matrix mu nu, of course, governs the strength of the internal interactions, and in particular, the off-diagonal elements will modulate the dependencies between the particles. And okay, to keep things simple, I will focus on the case of two particles, but really you can generalize this for as many particles as you want. So these off-diagonal elements are nothing but the pairwise interactions between the internal degrees of freedom, which we will refer to as internal interactions. But then, crucially, we also have an environment here, and we choose an archetypal environment, if you want, which is basically that the diffusion coefficient changes randomly in time. And in particular, this diffusion coefficient here is described by a dichotomous process in which the diffusion jumps between two states, D minus and D plus, with some rates W minus and W plus. And this description is quite simple, but it's actually very relevant in the context of inhomogeneous media, for instance, or diffusing diffusivities, in which particles experience random changes in their diffusion, as you can see here in this depiction, in which you have two particles interacting, going around in some space that has some patches at different temperatures, for instance. So they will experience random changes in their diffusion. Okay, so our aim now is to try to understand this system. So in this system, as we were saying, there will be two sources of dependencies: the environment, which will be quite complicated, and the internal interactions, which are linear interactions for the sake of simplicity. And in order to describe this system, let's start from a simple case, the case in which there are no interactions at all. So all the dependencies that we will find will be solely determined by the environment. So in this case, the probability distribution of our system is described by this mixed Fokker-Planck equation. But this Fokker-Planck equation is actually quite hard to solve in general. However, what we can do is we can consider some proper timescale separation limit and to try to understand if we can obtain the stationary distribution. So there are two obvious timescales in the system that are quite interesting. So one is the one of the environments, which is intuitively just how fast the jumps between the two states of the diffusion coefficients happens. And the other one is instead represented by this parameter here tau, which is nothing but the typical timescale at which the internal degrees of freedom relax to the stationary state. So in particular, we will be interested in the limits in which the jumps are either much faster or much slower than the internal relaxations. And let me start from the simple case, the case in which the environment is actually much faster than the internal dynamics. Because in this case, it turns out that a fast environment, which is perhaps unsurprising, only acts on average. That is, the degrees of freedom don't really fill the single jumps, but just an average diffusion coefficient. So the stationary solution is actually quite simple to write down, and it's simply a Gaussian distribution with this diffusion coefficient that is averaged on the states of the environment. So this limit, it's quite easy. The other one instead is actually the interesting limit, and it's the limit in which these jumps between the two diffusion coefficients are very slow with respect to the internal timescales, which means that the degrees of freedom have plenty of time to relax to their stationary state every time a single jump takes place. So the overall stationary distribution is the average of the two stationary probabilities weighted by this pi here, which is the stationary distribution of the dichotomous process, so that I basically indexes the states of the system. And again, for simplicity, I will often think about a case in which there are only two states, so I can be either -1 or +1, as in the plot before. So in this case here, we end up, the stationary distribution that we end up with is a mixture of Gaussian distributions with the different diffusion coefficients. All right, so now the question is, can we try and evaluate the information content, if you want, that is present in the system, and it is the information that somehow the environment is injecting in the particles that otherwise are not interacting? And it turns out that the answer is yes. So you can do it. You can compute some exact bounds and some. You also need a bit of Monte Carlo integration, but we can compute the mutual information between the internal degrees of freedom under the effect of this environment. And it turns out that this information that our two particles share due to the jumps between the different diffusion coefficients can actually be very, very different than zero. And it is represented here by this curve. And this means, as I was mentioning before, that the environment may induce a very, very strong dependence between the degrees of freedom. And this dependence is modulated by some dimensional parameters, for instance, d minus over d plus, which is basically telling you how much the environmental states are different, and w minus over w plus, which is basically telling you the persistence of the two environmental states. And so what we have here is that the environment is inducing these dependencies. So in a sense, it is injecting information, creating information between the two particles, an information that does not come from interaction itself. But of course, this information is not limitless. So in fact, it is upper bounded by the entropy of the jumps. And if you think about it, this is quite intuitive because the entropy of the jumps is a measure of exactly how much information is contained in the environment itself. So the key message here is that there is a bound on the amount of information, so the amount of dependencies that are created by the environment. And this bound is achieved when the environmental states are very different and when the jumps are really slow. And so this turns out to be quite interesting. Then we can actually try to understand what happens in the opposite case. And the opposite case, if you think about it, it's quite easy because the jumps are so fast that the single degrees of freedom don't really feel them. So, and this point will be quite fundamental later. This gray surface here, which represents the mutual information in the fast jump limit, is 0. So the mutual information between the 2 degrees of freedom vanish because the particles are only feeling an average effect, and thus there are no induced dependencies anymore. So, okay, we kind of have a very good understanding, a pretty clear picture, if you want, of the information content in the system without the interactions, which is a measure of the dependencies created by the environment. But what happens now if we introduce interactions back? And this is what goes on. So now the colored surface represents the mutual information of the interacting particles in the same environment as before, whereas the gray surface represents the mutual information in the presence of the environment only. And what you see here is that the net effect of interactions is actually quite easy. So you can do exactly the same calculations as before, and quite remarkably, you find that interactions only produce a constant shift in the mutual information that only depends on the off-diagonal elements of the interaction matrix, which are, of course, our internal interactions. So what we have here is something quite surprising, if you think about it. And it is that the mutual information in our linear system, embedded in this dichotomous environment, the mutual information is just a sum of 2 terms, one that only depends on the internal interactions and not on the environment, and one that only depends on the environmental parameters. And this is the fundamental results that we obtained, and you can find described in details in the PRL paper that I mentioned before. But why is this important? Well, it turns out that this kind of paves the way to answering the question that we started with. How can we distinguish whether 2 particles are really interacting or are dependent because they share the same environment? Now imagine that you may have, in an experiment, some control over the environment. For instance, the temperature fluctuations in chemical systems or external stimulations in neural systems. And imagine that now you can push this environment towards the fast jump limit. Well, it turns out that any non-zero mutual information that you measure in that limit is actually a fingerprint of this term here, so a fingerprint of interactions themselves. And in general, even if you don't have actual control over the environment, but you have an idea on what this environment is, you can try and put some bounds on the total information that this environment can create in your system, so on which kind of dependencies this environment can create between your degrees of freedom. And then if you're able to calculate or measure the mutual information and find that this is higher than you would expect, then again, that is a fingerprint of interactions. So ideally, information theory can help us understanding what is going on with our degrees of freedom, even though we don't really know if the dependencies that we are seeing are due to internal interactions or changing environments. All right. And now what we can also do, we can try to understand if information theory can help us about the other step. So the step of going from a complex to a more simple, possibly lower dimensional description of our system. So what information theory can tell us in this case? So what can it tell us about how to build this step and about its properties? And this is a work that we very recently put on arXiv, so you can find it here. I will be not too long on this, but the idea is that we consider again a rather paradigmatic but physically relevant case. The one of an underdamped particle whose dynamics is described in the full velocity position phase space, where gamma here is the damping coefficient and F is a generic force field. So in general, if you want to describe this system, you need to integrate these equations in the full phase space, and it can be complicated and whatnot. But more importantly, often it is the case that we are mostly interested in positions, or maybe we can only observe the positions themselves. So this is a nice example, because the idea now is that you, instead of describing all of your degrees of freedom, so all of your positions and all your velocities, you want to find some kind of effective description that works for the positions themselves, for the positions alone. However, in general, we cannot really write down Langevin equations for the position space alone. So the idea is that you assume that that some kind of effective descriptions exist, and now you want to fix these parameters, this new force field, which in general will be different from the previous one, and this new diffusion coefficient, and you want to fix these parameters in the best way possible. And of course, this effective model may be very much different from the original dynamics. So the idea really is to choose whatever model you prefer that may be of interest for you or may give you some kind of analytical insights, and to try to make the choice of the parameters of the model in a smart way. And this is where information theory enters the game. The idea is that our parameter theta that describe our effective model are defined by, we define these parameters in such a way that the overall information loss at all times is at each time is minimized with respect to the original observed space. So in general, to do so, what you do is you consider a given information metric M, which could be, for instance, the properly symmetrized version of the Kullback-Leibler divergence that we introduced early, and then you explore the space of all possible parameters and you choose the ones that minimize this quantity here. And by definition, given the form of effective model that you choose, this is the best you can do, really. And okay, again, as usual, actually, to keep things analytically tractable, we make a Gaussian ansatz, so that the overall information loss, which we call f of m, only depends on the mean and the variance. Although in principle, we can let go of this and consider the full probability distributions, of course, at the price of analytical tractability. And actually, this ansatz is not so wild because it's actually exact in the harmonic case. So let me show you briefly what happens when we map an underdamped harmonic process like this one, which depends on omega and these parameters omega and gamma, into another harmonic process, which only takes place in the position space, in which is fully described by this parameter W here. And this W here is the parameter that we have to tune by minimizing the information loss associated to this map. And let me show you what happens when you look at the optimal value of W as a function of the parameters of the original systems, gamma and omega. And as you see here, something quite surprising takes place. We find that in general, this parameter space is not continuous, but displays an abrupt transition as a function of the parameters of the original model. And this transition here appears, let's say, at low enough values of gamma, so low enough values of damping, and at some point disappears, but you see here that there is a kind of drastic change in behavior. And this is kind of interesting because it is reminiscent of a first order phase transition. If you think about this total information loss as a sort of free energy, because you have two minima appearing that correspond somehow to different phases of the effective model and that exchange stability. And crucially, we show that this quite surprising effect is a sole consequence of the constraint of minimizing the information loss. So in general, it is there if you want to define somehow optimal lower dimensional models and you want to preserve as much information as possible about the original models. So the idea here, if you want, is kind of a warning signal. preserving information is, of course, the best you can do when you seek lower dimensional or coarse-grained representations of more complicated systems. But it may give rise to unexpected singularities that are not present in the original model. And this is, of course, important in physical cases, but these lower dimensional representations are quite relevant in many different fields. So it's actually quite important. All right, that's about it. So let me briefly summarize what we did. So we showed that mutual information can help us disentangling internal interactions from changing environment, helping us discriminate between the two. And then what we showed is that if you want to use information theory to define optimal effective models, you can define these models in the best way possible, but preserving the most information about the original system can make these effective models unexpectedly singular. Okay, I'm done. So thank you very much for your attention. And let me, of course, thank in particular Daniel and Amos, without whom this work would have not been possible. If you want, you can download these two papers from the QR codes here. And of course, if you have any questions, I would be very happy to take them. Thank you very much.
Thank you, Giorgio, for the talk. Are there questions or comments? I have one question. I mean, the possibility of separating the effect of the, let's say, of the environment from the internal dynamics. I mean, in a sense, I mean, as you said, this can be done if you have information concerning the statistical property of the tubes, right? Because yes, if you do not have any external information about that, you should yes, not be able to.
Exactly. So the thing is that we showed that, so in principle, this information in the system is disentangled in form, in the sense that you have two independent terms. But of course, if the two terms are present at the same time, in general, there is no way you can know about it. So the idea is that you have to find ways around this problem. So one would be if you have some controls over the environment, and this is again very specific, for instance, to chemical systems or neural systems in which you can control temperature fluctuations, but of course not ecological networks, for instance, in which you can really control the climate or something. And in that case, if you kind of control the environment, you may tune the environmental properties so that to isolate the contribution from the interactions alone. The other approach is actually more general, and the idea is that okay, you need to have some kind of information on what you believe the environment is, or at least what general properties it has, and in that way you can derive some bounds on the amount of information that this environment can inject into the system. And then if you measure, if you have trajectories, you can estimate the probability distribution, the stationary probability distributions, the mutual information. And if this information somehow is higher than the bounds, it means that there must be some kind of interaction going on there. Of course, with real systems, things are very tricky, but in principle, you can do it, let's say, but it's not easy.
Okay. Any other question or comments? Perhaps I have a second one, and then which is you were citing the Kullback library.
Yes.
Let's say a divergence, and in fact it is asymmetric, and you said, I mean, you can symmetrize and so on and so forth, but sometimes the asymmetry of the Kullback is also informative. I mean,
yes,
you see, yeah. Do you see any case where you use this asymmetric aspect of the Kullback?
Yes, actually, let me see if I can show the screen again. So actually, yes. And it's related to the second part of the talk. So basically, okay, I think you can see it, but it started again.
Yes.
Okay, let me see if I can go somewhere here. Okay. So in general, this is what happens in the second part of the talk, in which you have this kind of transition in the optimal models, and this is the behavior for a class of symmetric divergences that you can consider. It turns out that, unfortunately, I don't have it here, that if you consider the asymmetric Kullback library divergence, of course, the results will change depending on which probabilities you are averaging into. So for instance, if you try to define your optimal model by averaging over the probability of the effective model itself, this transition is not present anymore because you're losing a lot of information since the very start. So what I mean by that is that in general, what is it? Okay. So in general here, what you want is that this P here is really the probability distributions that is the complicated one, and Q of X is the easy approximation, if you wish. So if you do things in the opposite way, you kind of find some funny effects that kind of erases these weird singularities that appear. So in general, yes, of course, you will get very different results depending on what you do.
Okay, thank you. Any other question? If not, let's thank again both Francesco and Giorgio, and thanks a lot for your seminar. Thanks for attending, and as usually, next seminars will be on the second Thursday of the next month in April. So if you are interested, see you again on April. Bye-bye.
Thank you, bye.